So we were doing independence, and what we will do is we had done this definition of independence as two events A and B are independent if probability of A and B is same as probability of A times probability of B. And the idea was this is different from the previous setup where we did last time was this where one event had a effect on the probability of another event given by these conditional probability formulae. But here, and we discussed this Polya-Learn scheme quickly, but here what happens is that two events are such that the occurrence of one has no effect on the probability occurrence of one. So we saw one example where we looked at the first toss and the second toss being ahead, and we saw immediately that the probability of A given B was same as probability of A, and probability of B given A is the probability. This led us to the notion of independence, which is probability of A given B is the same as probability of A, but that we write it as in this form. Probability of A and B is the same as probability of A times probability. So let me just comment a bit on the definition of 1.4.2. So let me just comment on this a little bit. So what I want to comment on is that what does this guarantee? So it guarantees two things. So what does star guarantee? Let's see the importance of star. Let's call this a star, a double star. So double star observations, let's say. So the observed double star are the following, that okay, first we observed clearly that star clearly implies the chance of A given B is the same as chance of A. So this provided probability of B is positive. And that similarly B given A is the same as probability of B. This provided probability of A is positive. So let's assume these two things. Let's assume that probability of B and probability of A are both positive. So they're meaningful events to understand. So now what else does it give you? So now if you look at the chance of probability of A and B complement, given B complement. So let's say this is all less than 1. So everybody is less than 1. So all events A and A complement, B and B complement all occur with good probability. So now here, we think of this as probability of A and B complement divided by probability of B complement. You leave the bottom as it is. The top person, you can use that the properties of probability we have shown, same as probability of A minus probability of A and B divided by probability of B complement. And that's the same as by double star, same as probability of A minus probability of A times probability of B divided by probability of B complement. And if you read out the algebra, that's the same as probability of A into 1 minus the probability of B. The whole thing divided by probability of B complement, and that's the same as probability of A times probability of B complement divided by probability of B complement, and we get the same as probability of A. So in some sense, the moment I know B doesn't affect the occurrence of A, B complement also doesn't affect. So similarly, one can show, let me look it up. Similarly, one can show that probability of B given A complement is also the same as probability of B. So in some sense, double star, if I call this as one result equal to double star, two results from double star, this is a third result from double star, and 4 results from double star. So in some sense, double star contains 4 equations. That is, probability of A and B, A given B is probability of A, probability of B given A is probability of B, Probability of A given B complement is probability of A, and probability of A B given A complement is also probability. So in some sense, so double star actually implies all the following: that A and B are independent by definition, but so are A and B complement, so are A and A complement and B, and A and B complement, and so there are one more, right? A complement and B complement. This I have not checked, but it also implies. So this is one kind of funky thing about one equation. So in the two case, double star implies what you intuitively understand. A doesn't affect B, then B doesn't affect A, B complement should not affect A, and vice versa. So why is this important? The idea is that this is important because suppose we wish to extend the notion of independence to many events. Extend the notion of independence to many events rather than just two events. How do we do this? So this is one thing I would like to understand right now, and I'll try and give an example by which you'll understand this. Right. So let's do three first before we come to. Let's just do three. We come to this idea. Suppose we have three events. Three events. A1, A2, A3. So one thing is to say, let's say, and we want to quantify independence. We want to quantify independence. So one thing is tempting. So from double star, it's tempting to say they are independent if probability of A1 and A2 and A3 is the same as probability of A1 times probability of A2 times probability of A3. So this is tempting to say this. But we should be careful now. This in the two case we got lucky. In the three case, this is a cautionary note. This is one way of writing independence for three people, but this may not imply A1, let's say A2 and A3 complement are independent. In the two case, somehow we had this notion and we could do the algebra properly and get it, unlike the two case, right? So, unlike in double star, where this actually implied everybody. So be a little bit careful now. You can't just take this. The second, this is one is approach A. The other approach is it's also tempting to say the following that okay, it's tempting to say okay, each pair is independent. So let's say it's tempting to say uh, uh, A1, A2, A3 are independent. If you don't want to say this, independent if A1 and A2 are independent, A1 and A3 are independent, and A2 and A3 are independent. So that is sorry. So this is something that one could think about. But this again has a cautionary tale. So let's see the cautionary tale. So this is like again. So it's known that pairwise independence. This is called pairwise independence. You assume that every pair is independent. So this typically does not imply independence. Okay. Let's this the first one. I'll let you see an example. This notion, let me try and see if I can give you an example. So let's do a simple example. Let's go back to our earlier one, the earlier example. Let's go back to our earlier example. So A was first toss. Sorry, A was the event that the first toss is ahead. Uh, B was the event the the second toss is ahead. And now let's say I have introduce an event C that let's say I have either head in the first toss or tail in the first toss, or tail head. Let's say tail head in the first two tosses. Let's say I take the event C like this. Now we have seen earlier A and B are independent. Now let's try and do the calculation. Let's try and do probability of A and C. That's the same as the A and C put together. You can just check. It's A and C means head in the first toss. So that's just going to be uh, 2 by 8, and that's just 1 by 4 because only two people are common. Probability of B and C is the same again as 2 by 8, which is 1 by 4. And you know that the probability of C is probability of A is probability of B is all half. So this will imply that probability of A and C is same as probability of A times probability of C. Probability of B and C the same as probability of B times probability of C. Right? That's just the fact. So therefore, A, C are independent, and B, C are also independent. So they are pairwise independent, right? So that means we have seen an example that is an example where A, B, and C are pairwise independent. But lo and behold, the following happens, right? But what happened now? Unfortunately, if you look at the event A and B and C, that means you have a head in the first toss, head in the second toss. So you're left only with two guys now. A and B and C is just head, 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 and head, head, tail. Right? That's just the way it's defined. Right? That's the way it comes out. So probability of A and B and C is going to be 2 by 8, which is 1/4. And unfortunately, this is not equal to 1/8, which is the same as probability of A times probability of B times probability of C. So we are goosed little bit. So this doesn't imply this crucial thing we wanted. Whereas if A, B, C are independent, then the probability multiplies up. So in some sense, we can't do this pairwise independence to the same as independence. Be very careful. It's a very important aspect of probability to keep in mind. So that leads us to a definition of independence for many events, which I'll explain now. So this is a crucial idea. So what is it? So now let's do a definition. So let's do definition 1.4.5. This is called mutual independence. So let me write it down properly. So a finite collection so let n be bigger than or equal to 1. A finite collection of events a1, a2 all the way up to an are mutually independent if I look at the probability of the intersection of events is same as the probability of product. So here I have to put many such cases. So let me put in a little bit of in green, let's say. So probability of EI the same as probability of EI, where I have to go through all possible combinations where EI are either AI or AI complement. So is the definition clear? So the idea is that you want n events to be independent, you have to check this equation for all possibilities of AI being AI complement, or with AI being AI. So AI being AI complement or AI being AI. So essentially that you have to check 2 to the n equations to check independence. And then you can say an arbitrary collection of events, arbitrary collection of events, AT, where T is in some index set I, for some index set I, are independent. So here what you do is, here you say, if for any finite subcollection, they are mutually independent. If for any finite subcollection, they are independent. Maybe if I want to put the correct English, I should say, if any finite subcollection of them is independent. So it's a crucial sort of idea. Independence means you must check these. Let's call this as triple star. So what are the observations? So the observations are the following. So triple star includes 2 to the n equations, not one equation. Unlike the n equal to 2 case, we didn't have to specify all 4 equations. One equation implied all 4. For n bigger than or equal to 3, it's not the case, as we observe. So let's just write the observations down. So one is that triple star actually has 2 to the n equations, right? Maybe I should write that in green, so its observations are clear. actually has 2 to the n equations. Uh, in n equal to 2 case, one equation probability A1 and A2 equal to probability of A1 times probability of A2 implied the other 3. And that's so that is one equation. Let me write it in English so it's clear. One equation that is double star implied the other 3. But this, as we saw in the example, this is not the case in not the case for n bigger than equal to 3. This is observation 1. So this is observation 1. Observation 2 is the following. Right. So A1, A2, AN are independent. This will actually imply any finite subcollection are also independent. So that is in the n equal to 3 case, A1, A2, A3 are independent will actually imply pairwise independence. But we already seen the reverse is not true. Pairwise independence doesn't imply this. Right? So this is one of the key sort of ideas of this phenomenon, that you have to be careful when this happens. So in the n equal to 2 case, you get lucky. This is recap quickly. We'll stop for the day. In the n equal to 2 case, you get lucky because this one equation implies all 4 equations. In the n equal to 3 case itself, it's not one equation. You need many more things. Just probability of A1 and A2 and A3 splitting up as a product may not be good enough. So what you have to do is, you saw an example where pairwise independence does not imply actual independence. So what we're going to have to do is, we have to go over all possible complements and events in the collection, and you have to check all equations are true. Only then you say the collection of events are independent. And the two observations are that to check independence for finite subcollection, you will actually need 2 to the n equations. And the advantage of this is that in one shot, these 2 to the n equations will also give you any subcollection independence. So one implication is obvious, but the reverse implication is not true. Okay. So even here, this is not true, right? This is not right. So this you have to be careful that going backwards is not going to be the correct thing. Going forwards is okay, but independence is a very crucial property. We will see many applications of it as we go on. So this finishes the sort of the basic concepts in probability in terms of. So let me just quickly recap what all we've done in this chapter. So let me just quickly recap and then I'll close for the day. So just a recap of this chapter. So one feature we did was we defined what a sample space was. We had an event collection of events. We had temporary definition so far, which we will keep for some time. Definition of events. So it's just as of now for us, it's just the power set of S, all subsets of S. We define P to be a probability, a function from F to 0, 1. It satisfied two things. The probability of S was 1, and if E, K are a disjoint collection of events, then probability of the union of I equal to 1 to infinity EI is the same as the sum from I equal to 1 to infinity of probability of EI. That's one thing we start off with. The second thing we discussed post that was this idea of equally likely outcomes. So that was the basis of our understanding and analysis after that. And we have a finite set, probability of S was finite, and the chance of any event A was the size of A by the size of S. The third concept we discussed was a conditional probability. And this include a key theorem called the Bayes theorem. And the fourth one was the notion of independence. And in between all this, we strung together these ideas of, from this, we had these other ideas that probability was finitely additive, that is, across finite unions, also the same thing happens. Probability of the empty set was 0, and we also had the fact that the probability of A union B was probability of A plus probability of B minus probability of A. These are some of the things that we've sort of done in this chapter. So now we will use this in the next chapter to sort of understand repeated trials of the same experiment and so on.